Hello everyone, this is the final presentation for Class CISC 520 Data Engineering and Mining from Chu Yutong and Yixuan. Our topic is mushroom classification. First, let's have a look of the data and problems we're going to solve. So from the top pictures, we could see the snapshot of our data. We downloaded our data from Kaggle. This data is originally contributed to the UCI machine learning repository nearly 30 years ago. Since mushroom hunting is still very popular and it's hard to decide if the mushroom is editable poisonous, we're going to build a model based on this data set. Our data have 8,124 entries and 23 columns. The most important column is the first column, which describes if the mushroom is poisonous or editable, like it indicated by P and E. We could also have a look of the mushroom, so it has like a cap, it have different shapes and different colors and different surfaces, and they are all different attributes of the mushrooms. So we're going to use this to predict if the mushroom is editable or poisonous and build models. This is a more detailed explanation of all the attributes, and for each column they have it shows their distinguished attributes. Like for example, for class, it has E and P, which means editable or poisonous, and for the cap color, it has characters like B, C, E, G, which means brown, cinnamon, green, or gray, or pink, or purple, or red. Since our data is letters and which is characteristics, so we are going to use the label encoding to convert all the unique values to integers. Thus we perform the label encoding on this data. Let's do some simple exploratory analysis about our data. First, we'll have a look of the distribution of the mushrooms by classes. So as we could see in this pie chart, 48.2% of mushrooms are poisonous in our data set, and 51.8% are editable mushrooms in our data set. This is more generally looking of the distributions of different columns. Some have a more different attributes, some have like less attributes. We could see for class 0 and 1, which is editable or poisonous. In this chat, we have a looking of how the cap colors variables data are in our data set. Like we could see in the first figure, brown, gray, red, and yellow and white is the most common color cap colors for mushrooms. And for brown and gray or wet mushrooms, there higher chance of being editable, but for red and yellow cap colored mushrooms, there are a higher chance of being poisonous. This is a looking of the odor of mushrooms. So usually non-odor have a higher chance of being editable, but like for foul and fishy and spicy odor, there are higher chance of being poisonous. This pie chart shows the different habitat type of mushrooms, like 38.7% living in woods and 26.4% grow in grasses. Since we encoded our data to numerical, then we scale our data to be between 1 -1 and 1 to further standardize our data. We did a simple principal component analysis. It is the process of computing the principal components and use them to perform a change of basis on the data, sometimes using only the first few principal components and ignoring the rest. In our situation, we could see the last 4 components has less amount of variance of the data. The first 17 components returns more than 90% of the data. We used only the first 2 components to do a k-means classification and colored it in the second diagram. So for our classification, we first did the data split. Train test split is to unknown data points to test the data rather than testing with the same points with which the model was trained. This helps capture the model performance much more better. The first method we use to build our model is logistic regression. So in statistics, the logistic model is used to model the probability of a certain class of event existing, such as pass of 4 or win or lose, which is binary data. So it's very suitable for our data cases, since we are going to classify the mushroom as being poisonous or editable. We could say like the AUC for this model is 0.99, which is pretty high. The true negatives we get is 815 true negatives, and we got 744 true positives. There are only 30 false positive and 36 false negative. Then we use a naive Bayes to build another model. This model has a slightly less AUC, which is 0.96, but it's still pretty good. We could also have a look of our true negative and true positives. Is all more than 45%. The last method we use is support vector machine. In machine learning, support vector machines supervise machine learning models with associated learning algorithms that analyze data for classification and regression analysis. In this model we built, we actually got a AUC of 1, which means the model works very well on our text database. It gets no false positive and no false negative. As a conclusion, by comparing the AUC of the ROC curves of 3 models, we use the support vector machine. One got the highest AUC, which is 1, and is the most accurate model among these 3 for our data. The models we created by using logistic regression and Bayes could also perform the classification at high accuracy. We did some data exploratory analysis and PC, but we didn't build our model with further future selection. For example, for the logistic regression, we could include more composition, like 70 more significant ones, to further tune our model and do some comparison. And we standardize all features to just numbers could have some further discussion as we did some native-based basic model, but we could also try algorithm native basis to further do comparison and choose a better model. This is our reference, and thank you.